Thank you for joining us this evening. You were brought into this session with your microphone and video off. If you have questions, please put it in the chat. We will collect them and address them to Jeff after his presentation. This program will be recorded and it will be made available on the Detroit Public Library YouTube channel and through Wayne State University's website. I am Jennifer Dye. I'm a librarian at the Detroit Public Library. We've had astronomy programs for several years, and before the upheavals of 2020, we had in-person programs. When things fell apart in spring of 2020, we put the programs on hiatus, and we finally launched them again in early 2021. We've been fortunate enough to work with Megan McCullen, director of the Wayne State University Planetarium. Unfortunately, she is a bit delayed. She usually helps me with running these programs. I do ask that if you have questions, you put them in the chat, and we will make sure that we ask them at the end of the program. Megan has been very helpful. Aside from helping to run the programs, she's been a link to the community of Wayne State University faculty and alumni. And one of those alumni is our presenter tonight, Jeff Macleod. He has a bachelor's in physics and astronomy. He's a former president of the Warren Astronomical Society. The Warren Astronomical Society, the best astronomy club in Michigan, his words, but I'm a member too. He is currently the observatory manager of the society. During his time at Wayne State University, he was active with their astronomy club, as well as a presenter at the Wayne State Planetarium. His grandfather first showed him the night sky, and he has been enamored with space ever since, with a special place in his heart for NASA, spaceflight mechanics, and astronomical simulations. All of his spare time is divided between his passion projects: doing astronomical outreach, performing dangerous juggling feats on a 6-foot-tall unicycle, and most recently, building a Gemini spaceship simulator you can climb in and fly, if you ask nicely. Jeff, thank you for joining us this evening.
Well, I'm glad to be here. And hopefully we can make an event for that simulator next year. So I am going to share my whole screen. So hopefully I can go to some of these links throughout the presentation. All right, can you guys hear me okay? All right, yeah. So it's been a while since I've done a virtual talk. I've been trying to avoid them, but I got the opportunity, so I figured I'd take it. This is one of my favorite presentations. It's a little different than what most people talk about when they talk about the moon. If you're new to astronomy, you might think it's crazy that someone would say that the moon was boring, but in the astronomical community, we actually do hear that. People take the moon for granted. It gets in the way of astrophotography. You know, people want to see the really dark, faint stuff that's really far away, and you got to do those on moonless nights. So the moon comes out and it gets in the way. Also on meteor showers, you don't want the moon in the way. It's going to brighten up the sky and you're not going to see as many of those faint meteorites. However, there's a lot of interesting things about the moon. This talk in particular is just going to focus on simple observations and subtle motions that you might not be familiar with the moon. So there's a whole other branch of just, lunar geology that's very interesting, lunar formation. The space flight history of the moon is also extremely fascinating, but unfortunately, it would take me hours and hours and hours to cover all of that. So what we're going to do in this presentation is roughly in some sort of order, cover misconceptions and illusions that pertain to the moon, librations, a word you may not have heard, but we'll talk about what that means, precessions and perturbations of the moon, and then finally eclipses and occultations. So a lot of these things that we're going to be talking about they kind of run into each other, so there's no great way to cover them. So I just kind of picked an order that made sense to me. So just to give you guys a little bit of a background.
Excuse me, Jeff, I wanted to
yes.
say I pinned you because which was a mistake, because now your screen is shrunken. So I unpinned you and you should
Okay.
be able to display it again.
Do I have to do anything?
I think you're going to have to. I've tried to unpin you and that wasn't
Okay,
enough.
should I stop sharing and then?
That might be best. Stop and
Okay,
then restart.
Let's see how that goes. We want the full screen. Is that any better?
Yes. Thank you.
Wonderful. All right, and I'm going to minimize that. Okay, not too much obscured. Can you see the Earth and the Moon? Sometimes there's stuff in the way. So this just gives you the main picture here, gives you the relative size between the Earth and the Moon. So the Earth is about a quarter of the diameter of the Earth, roughly 2,000 miles across. And then down here at the bottom, hopefully you guys can see my cursor. This is actually the Moon and the Earth at scale. So the Moon is quite farther away than most people would assume. It's about 30 Earth diameters. 250,000 miles is the number I usually quote, just to get a good ballpark. Next slide. So a lot of this orbital stuff we're not really concerned with, but we are going to be talking about inclination and eccentricity. So there's a lot of kind of subtle math things for defining orbits, but inclination is going to be the plane in which the moon is kind of going around. And then eccentricity is the shape of that orbit. And we'll talk about those in a little bit more detail as we get to them. But the first misconception that I want to cover is that the phases of the moon are caused by Earth's shadow. This is absolutely false. What's actually causing the phasing of the moon is the orbit of the moon itself. So if you look at this graphic, we've got the sun coming from very far away, illuminating half of the moon at all times. But as the moon is going around the Earth, you're seeing a different perspective of that illuminated surface. So the boundary between the light side and the dark side of the moon, we call the terminator. That is this line here. And another misconception that we can cover right now is that the moon doesn't rotate. We always see the same side of the moon, but this is a little bit of a misconception. The moon does rotate. It just happens to rotate at the same speed that it's revolving around the Earth. So again, if you look at this graphic, as the moon is going around the Earth, it is rotating such that the same side always faces the Earth. So if the moon truly didn't rotate, it would appear to rotate from our vantage point. And this is kind of a weird reference frame issue with the mechanics of free floating bodies in space. And then the last thing, this is not a misconception, but you can see that I can actually see the dark side of the moon lit up here. This is not a camera trick. You can actually observe this when the moon is in similar phases like this. This is a phenomena we call earthshine. It's one of my favorite kind of just naked eye observations to point out to people, because it's called earthshine because that side of the moon is not being illuminated by the sun, but is being illuminated by reflected light off of the Earth. So if we find this phase on our graphic here, that would be roughly this guy right here. Sunlight is coming into the Earth. The Earth is mostly illuminated from the perspective of the moon. So there's a lot of reflected light hitting this dark side, and then that light is bouncing back into your eye. And this also demonstrates just how bright the Earth is compared to the moon, that it can actually illuminate the dark side of the moon. So I highly recommend trying to look for that Earth shine when you see these almost first quarter and just past first quarter moons. Another misconception is that the moon is bright. So if you look at this photo in the center here, the moon looks very bright, but this all comes down to exposure rates, your camera settings. The moon is actually rather dark. If we look at Apollo photos, or this is a photo taken by a spacecraft at a Lagrange point well behind the Earth, moon is rather dark. And so you can see it's sometimes compared to aged asphalt. And so there's an experiment you can do if you have a camera a little bit nicer than a cell phone camera, something that you can actually adjust f-stops on. You can take a picture of the moon, save those camera settings, and then go out the next day, take a picture of some asphalt. And you might have to play with the settings, because if you got a good picture of the moon, you might underexpose the asphalt, or vice versa. You might get like this moon is completely overexposed. But you'll find that they're actually much similar in color than maybe your perception of the moon is. There's a mathematical term for how bright an object is called albedo. It's a number between 0 and 1. So 0 is completely black, 1 is completely white. The moon is somewhere between 0.08 and 0.12. So much closer to the darker side of the spectrum. The Earth is around a 0.3. For comparison, we have all these white clouds that are making us much brighter in appearance. So going back to that Terminator, the line between the light side of the moon and the dark side, this is a great indicator of if you're pulling a telescope out where you want to look on the moon. So this is 2 images of the same crater. This is Copernicus crater. It's roughly about 60 miles across. And you can see in the left image here, it looks kind of flat. It just looks like a ring. However, this right image is breathtaking. It looks like it's taken with a better camera, but it has nothing to do with the camera. It has to do with what time in the lunar cycle this photo was taken. So you get these very long shadows casting into the crater. That gives your brain something to work with in terms of depth and topography, and so you can really see all of this fine detail around the crater and along the rim here that you just cannot see with this other image. There's also features on the moon that you can only see about 1 day out of the lunar cycle. So the straight wall is a good example of this. It's I think it's a few hundred miles long, several thousand feet tall, and it only casts a good shadow for about 1 or 2 days. So that's a fun feature to look for with a modest telescope. There's also some real science that you can do with images like this. So, you know the distance of the moon, you know the size of the moon, you can measure the relative sizes of these craters. And so you can actually, using trigonometry, use these shadows, because based on its location and the phasing, you can figure out the angles of these shadows, and then figure out the height of various structures. So this this is called a rebound structure. When this meteor impacted the moon, some of that material then bounces back up and creates these mountains in the center of craters. That central structure is over 2,000 feet tall. And so I don't think you could actually get that accurate for yourself, but you could probably get in the ballpark. And this crater is over 2 miles deep. So it's an immense structure. It'd be a fantastic place to go if they ever start making trips out there. So we talked about orbital stuff. So the first one is inclination. This is, again, the plane that your orbit is kind of tracing out in space. So what I want to stress to you guys is that the moon does not go around the Earth's equator. and nor does it go around the Earth in the same plane that the Earth is going around the sun. This is known as the ecliptic plane. In this, it's just called the orbital plane of the Earth. It's actually slightly inclined, about 5 degrees from the ecliptic. And so that subtly changes where you might be able to see the moon on any given day. So I made a small plot here. This shows, down here at the origin, we're looking due south. We go to the left, we're looking east. The other way, we're looking west. This is kind of just a convention from astronomy. And then up to 90 degrees is looking straight up, the zenith. And so you may be familiar that the sun rises in the east, goes towards the south and is high in the sky, and then sets in the west. So in the wintertime, the sun from Detroit can get as low as about 18, 19 degrees above the horizon. But in summertime, it gets way up here, north of 65 degrees. But because of that inclination, the moon can be 5 degrees higher or 5 degrees lower. So these purple lines kind of map out, this is the region from Detroit where you can see the moon. So you'll never see the moon right on the horizon in the south. You'll never see it very high in the sky in the west or the east. It's going to be in this region. And it's always going to be within 5 degrees of the sun. So if the sun is following this path, this would be your summer solstice. The moon's going to be between 5 degrees, somewhere in this region. This line here represents your equinoxes. So that's when the day and night are the same duration. So the moon will be somewhere within 5 degrees of this line. So, if the sun is down here in winter, you're not going to see the moon way up high. Well, because the sun's out in the daytime and the moon's out in the nighttime, you will see it high in the sky. That's a slightly different phenomena. But if you actually trace out the line that the sun crosses in the sky, it will be within 5 degrees of that. So that other orbital parameter, eccentricity, this is another number between 0 and 1. So 0 meaning no eccentricity, you basically get a circle. A circle is a mathematically symmetrical ellipse. 1 would be fully eccentric and basically be an infinite line. We're somewhere in between. The moon's orbit is mostly circular. Its eccentricity is only 0.05 or so, but that's enough to make a difference. So these two images here basically show you the relative sizes of the smallest moon that you might see and the largest moon. So this is the super moons that you hear about in the media from time to time. I personally hate the term supermoon. The moon is great all the time. There's nothing really too fantastic about a supermoon as opposed to any other moon. And like I said before, a full moon is typically not when we do observations. So these are two pictures of a full moon. This is actually Copernicus crater that we were looking at earlier. This is when it doesn't look very striking. Tycho down here in the corner is about the only feature, in my opinion, that looks great during a full moon, because you can see these huge ray structures emanating from Tycho crater. But for the most part, anything that you'd want to observe during some sort of phasing where you get those longer shadows. But this difference in the smallest and largest moon is only 14%. So a lot of people tell me that they can tell when it's a supermoon, and I tend to not believe them, because seeing a 14% change of something that is only a half a degree in the sky is a rather subtle difference. However, because it's only 14% larger in diameter, but its area becomes much larger, a supermoon can be 30% brighter than this minimal moon. So in terms of brightness, maybe you can tell the difference between a normal full moon and a supermoon, but not in terms of its angular size in the sky. Misconception number, however many we're on now. is the dark side of the moon. The dark side of the moon is a Pink Floyd album and nothing else. There is no dark side, and I think even I've said dark side when I'm talking about the Terminator, the light side and the dark side. But that is changing. In a new moon, the dark side is the side that's facing us. So here are an image of the near side on the left and the far side on the right. And you can see they both get sunlight at certain times. So this is obviously when the far side is fully illuminated, and this is, you know, half a month later when the near side is illuminated. So we see the near side all the time. The only people who have ever seen the far side in person are Apollo astronauts. So this picture was obviously taken by a spacecraft that went behind the moon. And you can see they are very different from one another. And there's a lot of questions about why that might be. It was a huge shock to the scientific community in the late 50s, early 60s, when we got our first look at the far side of the moon. I believe the Soviets were actually the first to image the far side. You can see there's all these dark regions on the near side. These are called maria or seas. These are huge basaltic flows. So basically what we've learned through different experiments that the Apollo astronauts left on the moon, that the near side has a thinner crust than the far side. So the question is, well, why would the near side have a thinner crust? And there's a few ideas floating around right now. One is that early in the moon's formation, it was so close to the Earth was also still molten and so hot that it was basically blasting the moon. So much so that material would actually ablate off of the near side and then coalesce onto the far side. So you would get material stripped away from one and then deposited on the other, making the far side thicker and the near side thinner. I don't know enough about planetary morphography to give you an answer on the validity of that theory. Another one is just that the gravity of the Earth pulled the core of the moon closer to the Earth, making the near side thinner and the far side thicker. That idea, I would say, is pretty debunked now. That's kind of a tidal example, and that's not what we observe in tides on Earth. You get two bulges. So there's a, if you look at ocean tides, there's a bulge or a tide that points to the moon, and there's one on the other side of the Earth that points away from the moon, and then they kind of go around. So you wouldn't expect the near side to be thinner and the far side to be thicker. You would kind of expect there to be two bulges. The third theory, and kind of the one that I like the most, is that there was just a natural asymmetry in the moon during its formation, and then that allowed the moon to quickly tidally lock the way it is, always facing one side to the Earth. And that then after it was locked, you get this volcanism that brings all of these maria to the surface. You get, you know, a thinner crust. The volcanism is going to go through that thinner crust more easily, and so that's what we get. But there is still a lot of debate and a lot of open-ended questions about just the moon's formation in general. I should have mentioned in the background, we believe that the moon was formed by a large impact. Something about the size of Mars hit the early Earth, and they kind of merged some things, and a lot of this crustal material became the moon. And that's also still pretty contested. We don't have all the details. It's very hard to simulate. But now we can get into more of the visual illusions. So there's quite a bit to unpack in this slide. This is the moon horizon illusion, and I would be willing to bet that everyone has experienced this at some point in their life. You see a moon low on the horizon, it's orange, and it looks enormous. And you swear that the moon is actually bigger. But I'm here to tell you, it's not any bigger. So there's a lot of competing theories about what's going on here. And so we're going to kind of break them down. I'm going to go to my notes a little bit so I don't skip anything good. So the first is just that there's atmospheric distortion. So this is this photo all the way to the left here. That is not what's causing the moon to appear bigger. Atmospheric distortion is a real thing. You can see it in that image. It is distorting the shape of the moon, but it is not magnifying the moon. So, you know, a lot of interesting things happen with the atmosphere, but it's not going to just wholesale magnify an image for you. So that moon right there looks big because of how the photo was taken. It was taken with a telephoto lens to make the buildings appear big compared to the moon. So like it looks bigger. Now, the next one is called the flattened dome hypothesis. So that's this image on the top here. And this is kind of psychological. It's the notion that in your mind, things on the horizon are farther away than the ceiling of the sky. And this is kind of believable. If you are out on the ocean or you've got some really big expansive field that you're in, the horizon can sometimes appear to be farther away than the top of the sky. But you know, the top of the sky is kind of a weird concept to say, because you know that there's not a top of the sky. But the idea is that you perceive a flattened dome when in reality the moon is kind of more on a spherical dome, the way it's going around. And so if you project onto the flattened dome, it appears smaller. My only issue with this is that it doesn't seem like the moon is the right size on the horizon and it gets smaller. It seems like it's the right size and then it gets larger, but maybe that's just 6 of one, half a dozen of the other. The explanation I like the most is this next one. This is called the Ponzo illusion. And this is basically that object sizes are kind of interpreted by the things that they're around. So those two orange dots are the exact same size. However, this one appears larger because it's nested relative to smaller objects. So that's, you know, when the moon is low on the horizon, it's near to buildings, it's near to trees, it's close to things that you have a reference for. And then when the moon goes very high in the sky, it's essentially surrounded by these large voids and you don't have anything to reference against. And so it appears smaller. This is very similar to the relative size hypothesis. This is also a pretty well-established illusion. These are also two moons that are the exact same size, but this railway track is kind of tricking your brain into kind of perceiving this bottom one as being smaller and this one as being larger, again, because it's a forced perspective. It's telling your brain that this one is farther away, and therefore, if it's that big, it must be enormous. But this is an illusion that you can very easily get rid of. Oh, there's one more great one though. It's called the angle of regard hypothesis. I didn't have an image for it. This is the idea that the angle of your head determines the size of objects. It sounds completely crazy to me. When you look up in a room, I don't see my ceiling distorting. So it's kind of an odd notion. However, sometimes when we're out at stargazing events and we've got a low moon on the horizon that looks very big, we'll tell people to turn around, so face away from the moon, and then look through your legs upside down at the moon. Something about being upside down, you lose these references and the moon won't appear so big. But sometimes we do that just to see if people will follow our instructions and do something silly. But it really does work. It's very odd. Another way that you can completely ruin this illusion is to just look at the moon for too long. So I was doing a lunar observation program where you had to identify all of these Maria naked eye. And so you stare at the moon for a long time. And the longer you just look at the moon, it's an odd phenomena. It just shrinks and gets smaller and smaller and smaller. So if you want to keep big moons as a cool phenomena, don't look at them too long. But what I was going to say is, if you want to prove to yourself that the moon is actually the same size, you could probably do it with a cell phone camera these days. So when you see the moon and it's big, take a picture of it. And then a few hours when it's very high in the sky and it looks smaller, take another picture, put those pictures next to each other. The moons will be virtually indistinguishable in size, as long as you don't zoom one in, So this is a little more nuanced. This is called the Terminator illusion. And this is one that if you don't see it for yourself, you're probably not aware of it. I actually had a person bring this up to me and I had not ever noticed it before. But this is that, the terminator is determined by the sun, and yet if you look at the moon sometimes, it doesn't look like the terminator is pointing at the sun. So I'm going to focus you guys to these two pictures here. So in this tiny little box, you probably can't see it, that's the moon, and the sun is this really bright thing over here. So the sun is casting light onto the moon. So this is the line, and so the terminator should be perpendicular to this line. However, if I zoom in this tiny little moon and show you here, you can see that the terminator is actually pointing this way. So what's going on here? These lines should be parallel and they're not. This is a distortion in geometry. So the moon, or the sun rather, is about 400 times farther away than the moon is. So you can think of the moon as being close to us and the sun is being far away, and you're kind of drawing a triangle and things kind of distort. So the way you can solve this is by taking a panoramic photo, but aligning your camera to the terminator. So that's what I've done on this left image. You can see the flagpoles are sideways. That's because I've rotated the camera to match the terminator. And then I've moved, as I've taken this panoramic photo, because this is probably 45 degrees or 50 degrees of rotation. I've moved it in the direction of the terminator, and you can see I get a straight line to the sun and I get a match in the terminator. The easy way to verify that nothing spooky is going on here is in this top image. So you can see we've got the terminator of the moon. You're looking at the sun, they're not matching up. You're saying, what the heck's going on? Get a ball, tennis ball, basketball, doesn't matter. Hold it up in the same direction as the moon. So basically take your ball and hold it over the moon, and you'll see that the shadow on the ball matches the shadow on the moon. So here is an earth marble that I have, and you can see that the shadow line on this marble is identical to the shadow line on the moon, and that's because I've put the marble very close to the moon in this perspective. So you can't hold the ball behind you, then you're going to get something different. But simply holding a ball out in front of the moon, you can see that they perfectly match up. All the shadows are being caused by the sun. There's nothing weird going on. So this is another optical illusion that you can observe for yourself on a good night. You need a little bit more time to do this one because you're going to have to observe the moon basically over several hours to see this effect. But the moon kind of appears to rotate throughout the night, not rotating along its axis, but rotating kind of perpendicular to it. So this is the moon at moonrise, and you can see there's a large crater here, here, and here. So if I draw a line, it's almost horizontal. But then several hours later, that line has dipped, and then by moonset, it's almost pointing straight down. And this is caused by our vantage point on the Earth. I have a picture coming up that kind of explains this a little bit better, but if you maybe draw it out for yourself, you can kind of get a sense for what's going on here. This was done in Stellarium, but you can If you've got a decent cell phone camera or any camera above a cell phone that you can actually see some detail in the moon, just hold your phone up, level to the horizon, take a picture, wait 4 hours, take another picture, and you'll notice that the moon has rotated in that image, and that is actually caused by the Earth rotating, nothing to do with the moon. So that gets us through a lot of our optical illusions. So we're going to go into librations. Librations are not optical illusions. They are real phenomena that is happening, and it is caused by very subtle motions in the Earth-Moon system. So there's a couple here that we're going to go through. And then if there's time at the end, maybe I'll talk about, this is an exaggerated libration calculator that I programmed. So the first one is latitudinal libration. And so libration is just this perceived rocking motion of the moon. And it's not that the moon is actually rocking, but the phenomena is not an optical illusion. There is an explanation here. So this is just caused by that inclination of the moon's orbit. So that 5 degrees doesn't sound like a lot, but sometimes the moon is a little bit more above us, and so we see up under to the South Pole, and then sometimes it falls below us and we see a little bit more of the North Pole. So in these two images to the right, you can see Tycho crater here. It's pretty close to the limb of the moon in this picture, and then here you can see it has risen several degrees. So latitudinal libration can cause, let's see here, almost 7 degrees of tilting. And this is going to be in the vertical direction. So you'll either see more of the north or more of the south of the moon. The next one is longitudinal libration. This one's a little bit more subtle, but the effects are a little bit more dramatic. So this is in the other direction, the longitudinal. So you'll see a little bit more around the corner, left or right of the moon. And this is caused, I said earlier that the moon rotates at the same speed that it revolves. That's not exactly true, because again, the moon's orbit is not a circle, it is an ellipse. Sometimes it's closer to the Earth, sometimes it's farther away. And what that means is that sometimes the rotation outpaces the revolution and vice versa. So in this image to the right, there's an arrow, and that is showing you the near side center of the moon that's pointed at the Earth, and it's going to rotate the same amount in the same time. However, the moon's position along this circle does not go the same distance in the same amount of time. When we're close to the Earth, it goes faster, so you can see a large separation here. And when it's far away, it goes slower, so there's a shorter separation there. And so you can see what ends up happening is at the apogee, or when the moon is farthest away, the lines match up, the arrow points right with the dotted line. Same with at perigee, when the moon is closest to the Earth. However, at other points, they mismatch. And so here the arrow is outpacing kind of where you would expect the moon to be facing. So what you're actually doing is seeing a little bit more of the right corner of the moon. And then as it comes around, it gets lagged behind, and you see a little bit more of the left. And so in the images here, you can see there's a crater here right on the edge, or maybe this Maria here. You can see a dramatic difference. This crater right here is not even visible when the moon is in this other libration. So those two things conspire along with this diurnal libration, and it means that you can see about 60% of the moon's surface, whereas if it was truly static, you would only ever be able to see 50%. So this last one, diurnal libration, this is very similar to the effect that causes the moon to appear to rotate. So this guy down here, he's upside down. Why didn't they turn him? He's standing on his head. That's not right. When you're here, imagine we're looking top down. So this shouldn't be North America. It should be the North Pole. You start here, you look, and you can see a little bit more of the right side of the moon. And then, 12 hours later, you're over here and you see a little bit more of the left side. So that is a very small effect. It's only about 1 degree. And that libration is every single day. The other librations take a whole lunar cycle to see. These are every day. And they also depend on your location. So if you're at the equator, they're going to be a full degree. Where we are, they're less pronounced because the circle that we're kind of making is smaller. So if you're up at the North Pole, you get no diurnal libration because you're essentially not moving. You're at a fixed point. You can also kind of see for yourself, if you're standing here and you look, this side of the moon would be on the left and this side would be on the right. But if you're standing here and you're upside down, the moon's going to appear upside down as when you were on the other side of the Earth. So that's that moon rotation illusion that we looked at earlier. Now, this next one is also going to cause the moon to appear to rotate, but it's caused by a different reason. Now, this is the polar angle, or the position of the polar angle. This was a phenomena that I didn't come across until I was actually researching this talk. So it is virtually impossible to observe unless you're taking very rigorous observations of the moon, because you have to peel apart all these other motions to kind of see this. But what's causing it is the moon is, again, it's not rotating around the equator. It's on this inclined plane, and it has a different axial tilt than the Earth does. It's only tilted a little bit more than 1 degree. It's like 1.5 degrees. However, that is enough. Let's see. I used a globe here. I didn't have a moon globe at the time. But if you see, the Earth's axis tilted 23.5 degrees here. When you're looking at it off to the right, you get one perspective. As it rotates around, I'm making the same side of the Earth face us in each image the same way that the moon does. But because that polar angle appears to change as it's rotating around, you get this weird rocking back and forth of the moon. And so we're going to put all of this together. Actually, we're not going to. The Lunar Reconnaissance Orbiter team. And I actually got to speak with one of the scientists. He's the one who explained the polar angle libration. It's not quite a libration, but there's a lot to unpack here, and then we'll click this link. So here in the upper left, we have the distance that the moon is away. So right here, it's kind of on the outer track. And then right about here, that's when it's at its closest approach. So you can kind of see there's some thickness of this gray line. That's the difference between the closest and farthest that the moons get. You can also see there's a line here. This is the Earth and moon at scale. So it's kind of right in the middle. So this point will meander between the closest and farthest that the moon gets. And as the animation goes, you'll be able to see that the moon gets larger and smaller. Down here in the bottom left, these are our librations. So this circle here is going to be our latitudinal libration. So you can see right now we're seeing a little bit more of the south pole of the moon, and our longitudinal libration, we're seeing a little bit more of the right side of the moon. And then this angle here is that position of the polar axis. So you'll see this thing wandering around. So what the LRO team did is basically took images of the moon in the same position of the sky day after day after day after day for the whole year. And then you can actually tease out all of these librations and the pulsing of the moon getting bigger and smaller and the phasing changing. So I'm going to click this link. Let me know if it doesn't show up. Let's go full screen. And they have these for every year. I just have 2019 because that's when I made this talk. Oh, come on. Is that the best we can do? So you can see there, the moon rocking, it's getting smaller now. We're going into a new moon. That polar angle shifting to the right. Now we've got a crescent, the moon rocking back. If we look on the right side here, we can kind of see how that libration is taking effect. We can see the southern region a little bit more. The moon got really big, now it's going back small. So the moon kind of appears like it's just kind of always the same, but there are all these subtle motions that are going on that, for my money, you've never seen the same moon twice. It's always in a slightly different position, a slightly different angle, a slightly different libration, a slightly different phasing. And so it's truly more dynamic than a lot of people give it credit for. And we're not even done with all the things that are going on with the moon. So if you like this animation, they also have ones without all of these graphics going on. It's just the moon. They don't have like the crater name showing up, so it can kind of be aesthetically more pleasing to look at. And like I said, I believe they have these for, every year going forward. So let's go back to our presentation. All right, precessions and perturbations. So this is, again, the moon is ever changing. So there's 3 main precessions to the moon's orbit, and there's 6 major perturbations. So going through the precessions, very similar to how the Earth, we have an axial precession. This is the wobble of the Earth's rotation. That takes about 30,000 years to go around. The moon is much smaller, and it's not stabilized by anything. Our axial precession is actually stabilized by the moon. We don't stabilize the moon in the same way. So they have this nodal precession of about 18.6 years. And this is the plane of the moon's orbit. So the moon, we're in the center here and the moon's going around, but that plane is actually precessing the same way you would see a top wobbling. And so that changes where these, what we call nodes, where the moon's plane intersects the ecliptic plane. Those nodes are where eclipses take place. So this nodal precession, you have to understand it if you're going to predict eclipses. So there were ancient astronomers that got eclipses wrong, probably because they didn't know about this nodal precession. Then there is apsidal precession. This is the precession of the location of these perigee-apogee points where the moon is closest and farthest away. So if you see in this bottom left image, the moon is far, this is much exaggerated. The moon's orbit is nowhere near as elliptical and certainly not as close to the Earth, but the point at which it gets farthest away is also migrating. So every time it goes around, it's in a slightly different location. So, and that is on a nearly 9-year cycle. So every 9 years, that whole rosette pattern that's made comes back around. And then lastly, there's axial precession. This is exactly the same as the Earth's axial precession, the wobbling of our rotation. The moon just does it much faster. It's, again, 18.6 years, same as the nodal precession. They're kind of locked into each other. And so that 1.5 degrees of axial tilt that the moon has is also wobbling. The perturbations are a little bit more nuanced, and most of them are kind of talking about the same thing, but they were discovered at different periods in time, which is kind of interesting. So I like to give credit where credit is due. Equation of center was the first one, and this was actually known to the ancients. This is no longer a perturbation. This is understood physics now. This is that idea that because of that Keplerian motion that we looked at earlier, where the moon goes faster when it's closer to the Earth, if you are an ancient astronomer and you're under the assumption that the heavens are perfect, the moon is going around perfectly symmetrical, it will make the same distance every single day, and it will come back around to the same spot in 28 and a half days, whatever the lunar cycle is. However, if you actually look, it appears to speed up and then slow down and then speed up and then slow down, and that is because of that eccentricity of the orbit. So before eccentricity or orbits were really understood, it just looked like the moon was speeding up and slowing down in weird ways. And so the equation of center, basically, where the equation says the center of the moon should be and where it actually was different. But the ancients actually were able to figure that out. The next one is evection, which is basically very similar, and this is credited to Ptolemy. He's famous for his model of the solar system. So he's ancient Greek. The next one, variation. This is also the changing speed, and that's accredited to Tycho Brahe. Again, Keplerian motion. The annular equation is also Tycho Brahe, and that is the size of the moon's orbit changing. This is a pretty interesting one. So none of the orbits are perfect. The Earth's orbit is also an ellipse that gets closer to the sun and farther away. So we also speed up and slow down in our orbit around the sun. But what happens when we speed up, it speeds up the moon a little bit. And then when we slow down 6 months later, it slows down the moon a little bit. So, you've noticed this one perturbation, but if you get even more detailed measurements, there's an even more subtle perturbation that's on a 1 year cycle that's caused by the Earth around the sun. Then we get into really subtle perturbations that are caused by the other planets in the solar system and all kinds of crazy things. So an interesting one that the moon is causing for the Earth is we have our axial precession that we demonstrate as a top going around. But in fact, it doesn't trace out a perfect circle. It traces out a squiggly circle, because every time the moon's going around, it's pulling ever so slightly on our polar axis. So we kind of do this weird, very tight spirograph of circles within circles. The parallactic inequality is Newton just being Newton and being really, really darn smart and noticing some other very subtle perturbations of the moon's orbit. And then lastly, that reduction of the ecliptic. Basically what that is, all of these kind of cycles can be explained mathematically by sine functions. So all these different things you can map with different sine terms, and you can get a description of what the moon should be doing. So in the beginning of the 20th century, it was, I believe Newton had it in like the 20 to 30 terms. By the beginning of the 20th century, they had it up to about 1,400 terms. That means 1,400 different influences of perturbation. And now what they've been able to do with the retroreflectors that Apollo astronauts left on the moon is they've noticed all these subtle variations, and then they can fit mathematical models to that. And so now the number of terms is in the tens of thousands. So those tens of thousands of perturbations, they don't know what's causing them. They just know that, hey, when we make a mathematical model with this many terms, it very closely matches up to what we see with the moon. There's all kinds of other stuff going on. So for instance, the Earth or the moon is tidally locked to the Earth, meaning that the near side is always facing us. But I would bet you my paycheck that there is a subtle wobble where it's being tugged by Jupiter and it gets kind of misaligned and then it gets pulled back. So there actually probably is a very slight, I have no idea what the period of that oscillation might be, but these scientists probably know about it. So lastly, we'll kind of get out of the heady stuff and get into some stuff that's just around the corner. We've got some eclipses coming up. So this is, again, those node points where the moon's orbit crosses the Earth's orbit around the sun. And what happens is you can get the moon falling into the shadow of the Earth. This is a lunar eclipse. So you can see in this image here, these two dotted lines, this is the umbral and penumbral shadow. So there's kind of two shadows. If you look at this part of the image for a solar eclipse, you can see the two different shadows. And what's causing that is that the sun is not a point source. It has dimension to it. And really, if you look at any shadow closely, you'll see that there's a really fine fuzzy edge. And that is about a half a degree. So if you've got a very long shadow, that fuzziness can be rather large. So in the terms of the entire Earth, it's, thousands of miles wide. But if you have a very short shadow caused by your body, it's going to be a rather thin fuzziness. But there's a fuzziness to every shadow, and it is caused by the angular size of the sun in the sky. So we wanted to go through the dark part of the Earth shadow, the penumbral shadow. That's going to give us these total solar eclipses that are fun to observe. And then we have a solar eclipse, and that is when the moon passes in front of the Earth, in between the sun and the Earth. And so we've got on October 14th of this year, we have an annular eclipse. So this is a solar eclipse. However, the moon is going to be on the smaller side, and it's going to be too small to completely cover the sun. And so what you get is a ring of sun, and annular meaning ring, annular eclipse. So you will not see the corona like you will in a total solar eclipse, but you will see a ring of sun. And that one's passing through California down through New Mexico and into Mexico in October. However, then in April 8th of 24, we have a total solar eclipse coming across North America again. And that one's going to come up through Mexico, Texas, and then up into Ohio, and then out to sea. So definitely start planning your trips now for that, because total solar eclipses are fleeting in the continental United States, and so you gotta get them while the getting's good. And Ohio, although in April is not the best weather, I think it's worth a shot. So with that, I'm sorry, I always forget there's more. We have occultations. So these are like eclipses, but the moon is going to block other astronomical objects. So the moon, because it exists within 5 degrees of the ecliptic, it has the potential to block any of the planets besides the Earth. So we have some images here. This is the moon just before it covers up Venus, half covered Saturn. That is a beautiful Mars. And then here's a close pass of Jupiter and some clouds. Whoops, a daisy. And then this top right image, I think the star Aldebaran is actually blocked there. Aldebaran, the eye of Taurus, is the brightest star that the moon can occultate. So that's kind of the big one, but the moon occultates or passes in front of stars every night. So if you have a telescope, you can observe this. There's real science that can be done measuring these occultations. So in the image to the bottom right, this is the same event observed from different locations on the Earth. And what you can do between the timing of that and some three-dimensional geometry is you can figure out where the moon is in the sky. You can also, with grazing occultations, figure out the size of different lunar mountain ranges. So if you have, a star that's going to pass just along this northern edge, and you line up observers for several, tens of miles. You get an observer every mile for 50 miles or something crazy like that. And then they all record what the star did. The person to the north, the star never got blocked out. And then the person all the way to the south, the star got completely knocked out. But the people in the middle, the star would kind of blink on and off. And that's because it's passing behind mountains and then poking back out, because the terrain is kind of jagged. And so you can start to build up a map of what that particular mountain range looked like. So this was done hundreds of years ago to figure out sizes, exactly how big are some of these features on the moon. It was also used to determine that the moon didn't have an atmosphere, I believe in like the 1700s. If the moon had an atmosphere and a star was going to be blocked, it would dim out because the atmosphere would slowly block that light. And that's not what we observe. When a star goes behind the moon, it just snaps off. And then when it comes out from the other side, it turns back on. There's no dimming or slowly brightening because there just really isn't an atmosphere around the moon. So there's cool stuff. These are really cool events, and you can just kind of Google, my location, lunar occultations, and it'll tell you, hey, here's the next occultation of Saturn. Might not be for a few years, and that's why these are events that we really try to take advantage of when they come around, because they're a lot of fun, especially because you're not going to know what phase the moon is. So here you can see we've got a very thin, what would that be? A waning crescent with a lot of Earth shine. You can see the unlit side of the moon still, but there are other times like this you can't really see the moon, and so when Aldebaran disappears, you won't see it, and then all of a sudden it'll just come right on. Or I've seen one where it was going into the shadow of the moon, so you couldn't tell exactly when the star was gonna wink out, and you're waiting, and then all of a sudden it just winks out, and it's really cool. So I really like these. These are cool things, and again, parabinoculars, really, inexpensive telescope. You can see these kind of cool events. And with that, I'm actually done, and we can go into the chat and answer some questions.
All right, more questions are welcome. We have one from Ed Pank. I always found it curious the moon, being so close to the Earth, never developed an atmosphere and life. So do you have an opinion on that?
Well, I mean, you're not wrong to be surprised by that. There's a lot of mixing of material. We find lunar meteorites on the Earth, and I believe there's suspected Earth rocks that have been found either on the moon or Mars. So we know that there's cross-pollination between these objects. However, the moon, very early in its history, was just absolutely bombarded by being so close to the Earth that it baked virtually all the water out of it. There are still water deposits around the poles of the moon, but for the most part, it is a very dry, and it's really too small to get much of an atmosphere. There are examples of smaller bodies that have atmospheres, like Titan around Saturn, but it's an uphill battle for the moon to hold on to an atmosphere like that.
Well, thank you, Jeff. Does anyone else have any questions or comments? Looks like you covered absolutely everything, Jeff.
Okay, well, I'm still sharing my screen. What I'm going to do, if you'd like, I can show you this other animation. This is something that I put together. So we have these lunar librations, and they're pretty interesting. And so the question kind of got brought up, like, how crazy can this phenomena be? And so this is about as crazy as one could expect a libration to get. So there's a lot to unpack here. Can I pause it? Let's see here. There's a lot of math going on in this guy. I gotta find the variable that stops this darn thing. Where is it? Should be up at the top, but it's not. Ah, there we go. Pause this for a second. So imagine you're looking top down on the Earth. So the gray disk is the Earth, and so right here in the center would be the North Pole, and the black line would be the equator. And then if you've heard of geostationary satellites, this is what communication satellites, this is where they typically are. It is the point where an orbit is going to take 24 hours to go around. So if you put a satellite at the geostationary point, it will still be going around the Earth, but it will be going around the Earth at the same speed that the Earth is rotating. So these satellites don't appear to move in the night sky. However, they're so darn far away, you don't see them unless you're taking very careful photographs to find them. So if we press play, you can see that this red satellite is staying right over this point on the Earth, and they're just going to continue to go around. Now, the blue line is another satellite that has the same period of rotation, meaning 24 hours to go all the way around, but its eccentricity is not zero. So it's like the moon, it's non-circular. So those two satellites are going to meet up at these perigee and apogee points, but every other point they're going to be kind of wonky. So then you can see that the blue satellite down here is way outpacing the red one. But as they get out to apogee, they're going to match back up, and then they're going to do the reverse. The blue one's going to lag behind, and the red one's going to outpace. Okay. So then we change our vantage point without actually changing the graph and say, now, if you were on the Earth looking at the geostationary satellite, it would be the gray disk. It would just be motionless in the sky. Now, where would that other satellite be in reference to that one? That's the blue ball. And you can see, if we pause it here, I'm on the Earth, I'm looking towards the red one, the blue one is off to the right. Now I'm looking at that satellite, and the blue one is off to the right. And because of its lagging, I can see this dark region. That's what would be the far side of the moon rotating into my view. So this is a very exaggerated libration, and you can see the blue moon is going to get absolutely enormous in the sky. There's going to be this huge libration to the right. Then they're going to match up. It's going to go off to the other side. It's going to start to get small. There's going to be a libration to the left. It's exactly what we see with the moon, just way out of proportion, just crazy big. So that is a true supermoon right there. And you can see they've matched back up, and now the blue one's going to start outpacing. It's now to the left of the other one. It's getting smaller. So just a very exaggerated system. And what I find fun about this particular setup is, if you lived on this world, it would take you quite some time to figure out that that blue moon is not orbiting around the gray moon. It appears to, because it's getting smaller. It's going to go behind it. It's going to get bigger. It's going to go in front of it. You're going to get these weird eclipses happening between these two moons. But if you look at their orbits, they're just on two independent orbits. The blue moon is not orbiting the red moon or the gray moon. And so this is, again, subtleties in astrodynamics that stuff like this actually does happen. We've had some captured asteroid moons briefly. I call them little space potatoes or something, but we caught a moon for just under a year or so, and its orbit looked goofy because it was getting pulled by the moon and pulled by the Earth, and so it was just kind of wandering around in between the Earth and the moon, and then it got ejected. And stuff like that happens. We're getting better at detecting stuff like that, and we've seen it in Jupiter and some other objects. There's also a great story about, I think it's Apollo 12, the upper stage, this guy right here, the S4B, that actually boosts the spacecraft to the moon. They separate from that. On later missions, they purposely impacted the booster onto the surface of the moon. One, to set off little moonquakes that they could measure with the instruments that they had previously left, and two, so that they knew where it was going and they didn't have to worry about it. They didn't do that in Apollo 12, and it got slung out into a sun orbit by the moon, and it floated out there for decades, and then was briefly recaptured by the Earth and then flung out again. So the Apollo 12 S4B was briefly discovered as an asteroid, and it was like one of the highest albedo or brightest asteroids ever discovered, and had these crazy spectra of like, this thing is like a lot of titanium. What is going on here? And then they figured out that it wasn't an asteroid. It was the third stage of a Saturn V rocket that's been floating around the sun for 25, 30 years. So there's really interesting stories out there to find. But with that, if there's no other questions, I don't know.
Well, thank you, Jeff.
You are welcome.
I will give you the YouTube link again. It will take a few weeks before our marketing department gets it up.
No
I
worries.
used to have people follow me on Eventbrite, and the marketing department has decided that all of our programs are together, which means that the people who are following me get notices about every program that the library does. So if you would like to be notified of other programs, that you can send me an email. I usually hold these programs on the 4th Tuesday of the month. That's what I aim for when I'm scheduling.
Wonderful. And I'll do a quick plug for the Warren Club. If anyone's interested, the Warren Astronomical Society, we meet the first Monday of every month at the Cranbrook Institute of Science in Bloomfield. And then we meet the third Thursday of every month in Macomb Community College South Campus. And then the fourth Saturday of every month, we try to be out at the observatory for the evening to actually look at the sky, weather permitting. And then you can find us online, warrenastro.org, or just Google, my local astronomy club. You will find us. I got some other stuff coming up. This lecture is also on their YouTube, but when I gave it way back in 2020. So if there's anything that you kind of want to go back to and you don't want to wait for this one to get posted, you can check it out there. But yeah, go find us.
And I do hope to build a program in the spring around Jeff's Gemini simulation.
Yes, I wish.
So I'm looking for other realia to work with.
I wish I had some photos of it easily accessible. You can find that on Instagram. If you look for Gemini Simulator on Instagram, you should be able to find me.
Okay, well, thank you everyone for coming this evening. And I hope to see you later. And Jeff, thank you very much for coming. Good night.
Good night. Thanks.